Right now, beneath the Pacific coastline of Chile, two of the most dangerous fault segments on the planet are locked, storing decades of accumulated stress with nowhere to go. Not slowly releasing, not creeping, locked, completely. The kind of locked that geophysicists look at and use words like critically loaded and seismic gap. Technical language that, when you strip away this jargon, means the same thing it's always meant. Pressure building toward a breaking point. And the numbers attached to this particular breaking point are staggering. 19 million people live within the potential impact zone of what seismologists have identified as one of the most hazardous, unruptured fault configurations on Earth. The Atacama seismic gap, the Valparaiso segment, two tectonic time bombs sitting side by side on a coastline that has already, once in recorded human history, produced the largest earthquake ever measured anywhere on this planet. That's not hyperbole. That's the geological record. So what's actually happening down there? Why are scientists watching these particular segments so closely right now? And what does stress transfer actually mean for the 19 million people who wake up every morning not far from that coastline? That's what we're going to get into. All of it. The mechanics, the history, the monitoring data, and what the models are currently suggesting about where this is heading. Because here's what's important to understand before we go any further. This isn't a theoretical risk. This is a documented, measured, actively monitored threat that multiple research institutions have been flagging with increasing urgency. The question isn't whether these segments will rupture. According to the science, that's essentially certain. The question, the one that keeps seismologists up at night, is what happens when they do, and whether the rupture of one triggers the next. That chain reaction possibility. That's the part that changes everything. To understand what's at stake, you have to understand what Chile actually is. Not just a country, but a geological pressure cooker sitting directly on top of one of the most violent tectonic boundaries in the entire world. The Nazca Plate, one of the fastest moving oceanic plates on the planet, is diving beneath the South American continent at a rate of roughly 6.5 to 7 centimeters per year. That might not sound like much, but translate that into geological time and accumulated force, and what you get is a subduction zone that has produced more extreme seismic energy than almost any other location on Earth. Chile is, by a significant margin, the most earthquake-prone country on the planet when you measure cumulative seismic moment release. Not the most earthquake-prone in terms of frequency. Places like Japan and Indonesia generate more individual events, but in terms of raw energy released by single ruptures, Chile holds records that no other country comes close to touching. The 1960 Valdivia earthquake, which we'll return to in detail, released more energy than every other earthquake in the 20th century combined. Not every other large earthquake, every other earthquake combined. That's the system we're talking about. Now, the Chilean subduction zone doesn't rupture as one continuous fault. It breaks in segments, distinct sections of the plate boundary that behave somewhat independently, accumulating strain and releasing it on their own timescales. Scientists have mapped these segments over decades using historical earthquake records, GPS monitoring networks, and satellite-based geodetic measurements to understand which sections are currently locked, which are partially coupled, and which have recently ruptured and are in various stages of reloading. What makes the current situation particularly alarming is the configuration of what's locked versus what's already ruptured in recent decades. After major earthquakes in 2010 near Concepcion, the MW 8.8 mole earthquake, which was itself catastrophic, and in 2014 in the Iquique region and 2015 near Illapel, seismologists were able to map the stress redistribution across the entire fault system with much greater precision. What those maps revealed was not reassuring. There are segments, most critically the northern Atacama seismic gap, stretching roughly between 18 degrees and 24 degrees south latitude, and portions of the central Chilean fault near the greater Valparaiso region, that have not experienced a major stress-releasing rupture in a very long time. The Atacama Gap in particular has been identified as having not produced a great earthquake since at least 1877. That's nearly 150 years of strain accumulation on a fault segment that, based on GPS coupling measurements published by research teams from the Universidad de Chile and institutions like Caltech and GFZ Potsdam, is locked almost completely from the surface down to depths approaching 50 kilometers. Nearly 150 years. On a fault that historically ruptures roughly every century, you can do that math. And the answer is not comfortable. Here's the mechanics of what's actually happening beneath the seafloor. And it's more alarming than most people realize. When we say a fault segment is locked, we mean that the two plates in contact at that boundary are stuck. They're not sliding past each other the way you might imagine two tectonic plates moving, smoothly, incrementally, releasing small amounts of energy continuously. Instead, the friction between the descending Nazca plate and the overriding South American plate is high enough that the surfaces grip each other completely. No movement, no release. But the plates are still being driven together by the same forces that have always moved them. The mantle convection currents underneath don't care that the fault is stuck. They keep pushing. So what happens? The crust deforms. The overriding South American plate gets compressed, dragged down and inward along the subduction interface, and as years turn into decades, it accumulates what geophysicists call elastic strain energy. Think of it like slowly bending a green stick. The wood doesn't crack immediately, it bends, storing more and more potential. Energy until the strain exceeds the material's strength and it snaps. A locked fault segment is that stick. The longer it stays locked under ongoing convergence, the more energy it stores. GPS monitoring networks across northern Chile, dense arrays of continuously recording stations operated jointly by Chilean universities, the Centro Sismológico Nacional, and international research collaborations, have been measuring the surface expression of this locking for years. What they show is that the ground near the coast, in the Atacama region, is moving measurably towards the trench as the locked fault pulls it along with the descending plate. In some locations, surface deformation rates suggest interseismic coupling approaching values of 0.8 to 1.0, meaning nearly 100% of the relative plate motion is being stored as elastic strain rather than released through slow creep. 100%. Nothing is escaping. Everything is being saved up. Now, here's where stress transfer enters the picture. And this is the part that genuinely concerns scientists working on fault interaction models. When a neighboring fault segment does rupture, it doesn't just release its own stored energy and stop. The sudden displacement of one section of the plate boundary instantaneously redistributes stress across the entire surrounding fault system. This is called Coulomb stress transfer, named after the mathematical framework used to calculate it, and the implications for adjacent locked segments can go in one of two directions. Sometimes a rupture relieves stress on a neighboring segment. The movement actually reduces the forces acting on the adjacent fault. But in other configurations, particularly when one locked segment is directly adjacent to another and shares similar locking geometries, the rupture of the first can actually increase the stress on the second. It loads the neighboring segment. It moves it closer to failure. Seismologists from institutions including the USGS Earthquake Hazards Program and research groups at the University of California have published multiple studies examining exactly this phenomenon in Chile, and the findings point toward a deeply concerning pattern. The 2010 Mall earthquake, for example, appears to have increased Coulomb stress on portions of the central Chilean fault to the north. The 2015 Illapel earthquake, a magnitude 8.3 event, ruptured a section adjacent to areas that GPS data suggested were already critically stressed. Each of these events has effectively shuffled the deck of stress distribution across the entire system, and the analysis suggests that the remaining locked segments, particularly in the north, may have been loaded further by each of their neighbors' failures. There's also a secondary mechanism worth understanding: slow slip events. These are brief episodes, lasting days to weeks, where portions of the locked interface slip aseismically, meaning without generating felt earthquakes. Research published in journals including Nature Geoscience has identified slow slip events occurring on the deeper portions of the Chilean subduction zone, and some models suggest these events can themselves transfer stress upward onto the shallower locked portions of the fault. incrementally nudging already critically stressed segments toward the threshold for dynamic rupture. Scientists can't predict exactly when any individual rupture will occur based on slow slip alone. The relationship is complex and not yet fully understood. But the detection of these events adds another layer of concern to an already tense system. What all of this comes together to describe is not a fault segment sitting passively, simply waiting. It's a segment that is being actively loaded from multiple directions, by ongoing plate convergence, by stress transferred from neighboring ruptures, and potentially by slow slip occurring on adjacent, deeper portions of the fault. The word scientists use, and it's a word that appears repeatedly in the peer-reviewed literature on northern Chile, is mature, as in, this segment is seismically mature, as in, it has accumulated enough strain that rupture is geologically overdue. Chile knows exactly what happens when these faults finally let go, and the historical record is a warning written in ash, rubble, and missing coastlines. The most recent major rupture in the northern Atacama region occurred on May 9, 1877. It was a devastating event, estimated at magnitude 8.8, based on historical accounts and later analysis, producing a tsunami that was recorded not just along the Chilean coast, but across the entire Pacific basin, reaching Japan, Hawaii, and New Zealand, with measurable wave heights. The Chilean port city of Iquique was largely destroyed. Accounts from survivors and contemporary journalists described the sea withdrawing suddenly from the harbor, a phenomenon we now understand as the drawback phase of an impending tsunami wave, before returning in surges that inundated coastal communities and left widespread destruction. But even that event, catastrophic as it was, pales in comparison to what the geological record shows this system is capable of. On May 22, 1960, at 3:11 in the afternoon local time, a rupture began along the Chilean subduction zone, south of what is now the fully reloaded segments we're discussing today. What followed was unlike anything in the modern instrumental record. The fault unzipped along approximately 800 to 1,000 kilometers of plate boundary, an almost incomprehensible length, releasing energy equivalent to roughly 178 billion tons of TNT. The moment magnitude, 9.5. The largest earthquake ever recorded by scientific instruments. Within hours, a tsunami was crossing the Pacific at the speed of a commercial jet aircraft, 700 to 800 kilometers per hour in open ocean. In Chile itself, the waves reached heights of 25 meters in some coastal embayments. Cities were erased. Approximately 1,655 people died in Chile from the earthquake and tsunami combined, a number that, given the scale of the event, actually reflects how sparsely populated many affected areas were. The same tsunami killed 61 people in Hawaii, 138 in Japan, and 32 in the Philippines, despite traveling thousands of kilometers across open ocean. Now think about that in the context of today. The segments we're discussing, the northern Atacama Gap and the central Chilean segments near Valparaiso, sit directly adjacent to coastlines that are dramatically more densely populated now than they were in 1877 or even 1960. The Greater Valparaiso region, which includes Valparaiso itself, Viña del Mar, and the extended suburban coastal zone, is home to approximately 1 million people. Iquique and Antofagasta together represent hundreds of thousands of additional residents, and Santiago, the capital city of 7 million people, sits roughly 100 kilometers inland from the coast near Valparaiso, close enough that a great rupture in that segment could generate strong to violent shaking across the entire metropolitan area. The 2010 Mall earthquake, which ruptured a segment somewhat, to the south, provides a useful modern case study. That magnitude 8.8 event killed 525 people, displaced approximately 2 million, caused an estimated $30 billion in economic damage, and generated a tsunami that damaged coastal infrastructure from the Bio region northward. And critically, the Mall earthquake ruptured a section of the fault. That was considered somewhat less mature, less locked, and storing somewhat less accumulated strain than what scientists currently believe exists in the Northern Gap. Let that sink in. A less loaded segment, to the south of the area of greatest concern, produced one of the costliest natural disasters in Chilean history. The segments scientists are watching most carefully right now have been accumulating strain for decades longer, in some cases nearly a century and a half longer. What makes the current situation particularly alarming is what monitoring networks are actually detecting right now along these locked segments. Chile operates one of the most sophisticated seismic and geodetic monitoring systems in South America, a reality born partly from hard experience. The Red Sismológica Nacional, operated through the Centro Sismológico Nacional at the Universidad de Chile, runs hundreds of seismic stations across the country, feeding real-time data to analysts who watch for precursory signals, swarms, rate changes, slow slip events, and any indication that a locked segment may be entering a pre-failure phase. What those networks have been recording over the past several years warrants serious attention. Background seismicity in the northern Atacama region has not been quiet. Small to moderate earthquakes, events in the magnitude 3 to 5 range that alone would barely make headlines, are occurring with a frequency that researchers note is consistent with stress being concentrated at the edges of the locked zone. These edge zone earthquakes aren't random. They tend to cluster at the transition between the locked portion of the fault and the adjacent zones of partial coupling, exactly where mechanical models predict strain should concentrate as the locked segment loads further. GPS monitoring data, updated regularly through international collaborations and published by groups including researchers at the Institut de Physique du Globe de Paris and the GFZ German Research Center for Geosciences, continues to show interseismic locking at values that indicate the Atacama Gap is storing rather than releasing strain. The surface velocity fields, the measurable horizontal and vertical movement of monitoring stations across northern Chile, match very closely, with the patterns expected from a fully locked megathrust segment accumulating stress at the plate convergence rate. The Chilean government, through SHOE, the Servicio Hidrográfico y Oceanográfico de la Armada, and the National Emergency Management Agency CENEPRED, has invested significantly in tsunami warning infrastructure along the northern coast following the 2010 and 2014 events. Evacuation route signage, community drills, and early warning systems connected to the Pacific Tsunami Warning Center now represent a substantially improved preparedness landscape compared to 1960 or even 2010. Coastal communities in the Iquique region have conducted large-scale evacuation exercises, and public awareness of tsunami risk has been actively cultivated. But gaps remain. Urban development has continued in coastal zones across northern Chile, despite the well-documented risk. Some of the highest value real estate in cities like Iquique and Antofagasta sits within tsunami inundation zones that scientists and emergency planners have identified as high risk. Infrastructure, ports, water treatment facilities, hospitals, transportation corridors, in many cases has not been hardened to the level that the modeled threat demands. And crucially, the scale of a potential rupture in the northern seismic gap could exceed what even the improved warning systems were designed to manage in terms of the sheer speed and energy of a near-field tsunami. When the fault is directly offshore, sometimes less than 100 kilometers from the coastline, the time between rupture and first wave arrival can be as short as 15 to 20 minutes. In some coastal geometries, even less. Scientists can't predict exactly when a rupture will occur. That's a fundamental limitation of earthquake science that no monitoring system, however sophisticated, has yet overcome. What they can do, and what the literature is increasingly clear about, is characterize the probability. A 2018 study published in the journal Geophysical Research Letters estimated the probability of a great earthquake in the northern Chile seismic gap within a 50-year window at values that should command immediate policy attention. Other analyses, incorporating updated coupling models and stress transfer calculations from the 2014 Iquique and 2015 Illapel events, have suggested even shorter recurrence expectations. If the northern Chile seismic gap were to rupture, and the scientific consensus is that this is not a question of if, but when, the cascade of consequences could be staggering in ways that extend far beyond the immediate shaking. Let's think through what the models suggest, using the conditional language that responsible science demands, because the honest answer is that no one knows exactly how this would unfold. What we have are scenarios, probability-weighted, physically grounded scenarios, and some of them are deeply sobering. A rupture of the full northern Atacama Gap, which models suggest could potentially reach magnitude 8.8 to 9.0, depending on how much of the locked zone fails simultaneously, would generate shaking that could affect an area stretching from southern Peru through the Atacama region and into parts of central Chile. Strong to very strong ground motion, Mercalli intensity 7 to 9, might be experienced across an enormous area, with violent shaking possible near the rupture zone itself. Infrastructure not built to current seismic codes, and significant portions of older building stock in Chilean coastal cities were not, could face severe damage or collapse. But it's the tsunami that potentially poses the greatest threat to life. Near-field tsunami modeling by researchers at institutions including the Universidad de Concepción and international groups working through the NOAA Pacific Marine Environmental Laboratory suggests that a megathrust rupture in this region could generate initial wave heights along nearby Chilean coastlines of 10 to 20 meters or more in some locations, with higher values possible in coastal embayments and canyon mouths that focus wave energy. The Chilean coast north of Antofagasta has significant stretches where urban areas extend close to sea level and where natural topography provides limited protection from ocean inundation. The secondary effects multiply from there. A tsunami of this potential magnitude would radiate across the Pacific, reaching Peru within minutes to an hour, putting coastal populations in Ecuador, Colombia, Mexico, and Central America at risk within 1 to 3 hours, and potentially impacting Hawaii and the broader Pacific Basin within hours after that. The 2011 Tohoku tsunami in Japan, generated by a magnitude 9.1 earthquake on another subduction zone, provides a sobering reference point. That event killed nearly 20,000 people, despite Japan having some of the most sophisticated tsunami warning and barrier infrastructure in the world. The trans-Pacific implications of a comparable Chilean event would demand coordinated response across multiple countries simultaneously. Economic consequences could also be significant at a scale that extends far beyond Chile's borders. The Atacama region hosts some of the world's largest copper mining operations. For all, Chile produces roughly 27% of global copper supply, and infrastructure damage to mining operations, port facilities, and transportation networks could send shockwaves through global commodity markets. The port of Antofagasta alone handles enormous volumes of mining exports, and its location in the potential impact zone of both strong ground shakings and tsunami inundation raises concerns about supply chain disruption that analysts have noted, but that receives far less public attention than the human toll. And there's the stress transfer question, the one that ties this all back to where we started. If the Atacama Gap were to rupture, what would that mean for adjacent segments? Models examining Coulomb stress changes associated with a hypothetical northern rupture suggest that stress could be transferred both northward toward the Peru-Chile border region and southward toward the already partially loaded central Chilean segments. The possibility that a great earthquake in one segment could accelerate the loading and potentially trigger adjacent segments is not a fringe concern. It's a recognized feature of how complex fault systems behave, documented at subduction zones around the world. And it's one reason why researchers examining Chile don't look at any single segment in isolation. The domino possibility, not guaranteed, not inevitable from any single rupture, but physically plausible, and in some stress transfer calculations, not even. Particularly unlikely depending on the geometry and magnitude of the initiating event. Understanding the locked segments beneath Chile isn't about living in fear. It's about understanding that the ground beneath some of the most populated coastlines on Earth is operating under physical constraints that don't care about politics, economics, or the fact that 19 million people have built their lives nearby. The science here is robust. The monitoring is serious. The historical record is unambiguous. And the conclusion that emerges from all of it is not that catastrophe is certain or imminent in any time frame that allows for precise planning. Scientists are genuinely clear about that uncertainty. But that the risk is real, it is documented. It is actively being studied by researchers at world-class institutions, and it deserves to be taken seriously by everyone in a position to act on it. What can awareness actually do in the face of a geological force this large? More than you might think. The difference in outcomes between the 1960 Valdivia earthquake and the 2010 Mall earthquake, accounting for population differences, and the segments involved, reflects decades of improved building codes, better public education, enhanced warning systems, and community preparedness investment. Those improvements are real, they are measurable, and they matter enormously to the people who survive rather than don't. Chile has, in many respects, become a global model for seismic risk management. The country's investment in earthquake-resistant construction, community tsunami drills, and early warning infrastructure represents a serious institutional acknowledgement of what the geology demands. But the gap between current preparedness and what a worst-case northern Chile rupture might deliver remains significant. And that gap is not narrowing on its own. There's another fault system that deserves attention in this same conversation. One that researchers argue has been receiving insufficient focus despite displaying warning signs that parallel what we see in Chile. We'll be getting into that in the next video, and if you're following this type of analysis closely, you won't want to miss it. If what you've just heard concerns you, and it should, at least enough to make you want to know more, the most useful thing you can do is stay informed. Not anxious, informed. There's a meaningful difference, and it matters. Subscribe if you want to keep up with this kind of scientifically grounded analysis of geological threats that the mainstream conversation often underweights. Drop a comment below with where you're watching from, particularly if you're anywhere along the Pacific coast, because the community of people paying attention to this is more important than you might realize. The fault doesn't negotiate, but understanding it is a start.